Welcome to Math 201. This is our lesson where we're going to review 4.3 and 4.6. Do note that there are other sections in chapter 4 that will be on the next exam, but these two sections tend to be the trickiest, so they're getting their own review day. We've now learned to solve two different types of calculus word problems, related rates and optimization problems. And we've got a worksheet or an activity called opticrization to help you determine which is which. So you're going to start with the activity, optimization, and pause the video, try the problems, come back and press play when you're ready to go over them. What keywords appear in an optimization problem? So optimize, usually they ask you to either maximize or minimize, or find the smallest or largest, or shortest or longest, or fastest, okay, etc. They're asking you to find the most of something, the biggest, the smallest, etc. Okay, number two, when dealing with an optimization problem, what are the key steps to get started? Okay, so we want to provide as much detail as we can. So we want to write an equation to optimize. And then you also are going to need to identify a constraint equation. Oh, and you use the constraint to write the equation to optimize in terms of one variable only. Okay. Then you take the derivative of the equation to optimize and set it equal to 0 to solve for critical points. So find critical points by setting the derivative of the equation to optimize equal to 0. And then last, determine if any critical points or endpoints of the domain are maxes or mins. Okay, number three, what are keywords that appear in a related rates problem? So we typically see the word rate somewhere, or speed, or changing, increasing or decreasing, because those are just specific ways of changing. And they might ask about like how fast something is happening. What are the key steps in a related rates problem? So first thing we want to do is draw a dynamic picture. So you draw a picture of the situation they're describing with changing quantities labeled as variables. Okay, next, we want to identify what you know and what you want to know. 3, we want to write an equation that relates the variable you know something about and those you want to know about. And I'm just going to call those our important variables. Okay, the important variables are those that you know something about and those that you want to know something about. Okay, step 4 is take ddt of both sides. 5, we're going to redraw our picture at the specific moment in time. At the moment of interest. Okay, and then finally, plug in what you know and solve for what you want. Below is a mix of optimization and related rates problems. We want to identify what each type of problem is and give the function that you'll optimize and its domain, if it's optimization, or the relationship you'll differentiate for related rates. Okay, so first question. When a resistor of R ohms is connected to a battery of E volts with an internal resistance of R ohms, the power in watts in the external resistor is P equals E squared or capital R over capital R plus little r squared. If E and little r are constant, what value of capital R maximizes the power of the external resistor? So I see this word maximizes and we're going optimization. Okay. So if I want to optimize this, um, we are supposed to, for the optimization problems, we're supposed to give the function we want to optimize and its domain. Okay, so the function I want to optimize is P equals E squared capital R over capital R plus little r squared. And its domain, let's see, little r is a constant. So capital R is my input variable. So I want to know what are the possible values for capital R. And without knowing much about batteries and volts and stuff, I'm pretty sure you can have uh, capital R, you can have 0 ohms and it can go up to infinity. Okay, it has to be positive, like the smallest um, amount of resistance you can have is 0. Okay. Um, The very last question in this activity is to come back and solve each of these optimization problems. So I'm just going to, and related rates problems. So I'm just going to go ahead and solve this now before we move on to the next one. Okay, so if I want to optimize a function, I take its derivative and set it equal to 0. So I'm going to take p prime and its derivative, noting that capital E and little r are constants. Those are just numbers. So the derivative of E squared r is just E squared. So I'm going to have to do the quotient rule to take this derivative. So I'm going to have f prime, that's the derivative of my numerator, which is E squared. So that's f prime g. G is just the plain old denominator, doing nothing to it, minus f, which is E squared r times g prime, and the derivative of my denominator, remember, little r is a constant. My only variable is capital R. So I'm going to have to bring the 2 down. So I'm going to have 2 times capital R plus little r to the first. And then the derivative of the inside is just going to be a 1. 1 plus 0, so 1. I'm not going to write, I guess I could write that just to show that I did do the chain rule. Okay. And that's all over the denominator, which is capital R plus little r squared squared. So it's going to be raised to the fourth power. And I want to set that equal to 0. That's how we optimize stuff. We take the derivative, we set it equal to 0. Now, the only way a fraction can equal 0 is if its numerator equals 0. So I don't even have to worry about this. I'm going to go to a new slide and I'm going to set this numerator equal to 0. Okay, there's a little bit of tricky algebra here. So I have two terms. Here's a term and here's a term. I want to factor out anything that they have in common. They both have an e squared and they both have an r plus r, big R plus little r. So I'm going to factor out e squared and a big R plus little r. Okay, and what's left when I factor that out, here I took out the e squared. I took out one of these r plus r's, so I still have one left, capital R plus little r. Okay. Then I have minus. Over here, I already took out the e squared, and I already took out this r plus r, so I'm left with a big R and a 2. And set that equal to 0. And then I have two factors that I'm multiplying together, and the answer is 0. So either e squared times r plus r equals 0, or r plus r minus 2r equals 0. Now, in this case, e squared is a constant, so I could just divide it out. So I have big R plus little r equals 0. Remember, little r is a constant. Big R is my independent variable. So that's what I'm solving for. I'm solving for big R. So I get capital R equals negative R. And this never happens because we can't get a negative for our resistance. Now, my other equation, I want to solve for big R. So I have capital R minus 2 capital R is negative R. So I have negative capital R plus little r equals 0. And that means that capital R equals little r. That is my critical point. And then I just look at the critical points and the endpoints of the domain and see which one gives me my maximum. So I'm going to have big R and I'm going to have P. And remember, my function P is e squared R over r plus little r squared. Okay, and my critical point was R. And the endpoints of my domain were 0 and infinity. Okay, if I put a 0 in here for big R, you get 0 over something which is 0. If I think about what happens as big R goes to infinity, you would get the numerator goes to infinity, and so does the denominator, but it's going to be big R to the first in the numerator and big R squared in the denominator. So the denominator is going to go to infinity faster, and this will go to 0. You could write it out with L'Hopital's rule if you want, but that ends up going to 0. And then if you put in little r for big R, you get e squared little r over 2r squared, which is 4r squared. And that would simplify to e squared over 4r. So let me simplify that. E squared over 4r. And that is a positive value, so that is our max. So max power when big R equals little r. The ideal gas law relates pressure in atmospheres, temperature in Kelvin, and the volume in liters of a gas. The law states that PV equals RT, where R is the gas constant, uh, whatever that number is. And we're going to suppose that pressure is held at a constant 0.75 atm. If the temperature is allowed to increase at a constant rate of a half Kelvin per second, how fast is the volume changing when the temperature reaches 350 Kelvin? Okay, so we're getting words like increase and rate and how fast. This is going to be a related rates problem. So I don't have any picture to draw here, but I have an equation PV equals RT. That is going to be the equation that relates all my important variables. Now let's see if we can write out some stuff that we know and some stuff that we want to know. Okay, so pressure P is being held constant at 0.75. Okay. Temperature is allowed to increase, so that's the rate of change of temperature. So dT dt, capital T for temperature, little t for time, at a constant rate of 0.5 Kelvin per second. How fast is volume changing? So we want dV dt when temperature, capital T, is 350. And then I'm going to use my equation that relates all my important variables. So important variables are P, T, V, and R is in there too, but that's okay. We've got an extra variable. Okay, so I have PV equals RT, and R is actually a constant. It's 0.0821. So I could put that in if that makes things clearer. And P is also, we're holding that constant, so maybe I'll put that in too. So I have 0.75 V equals R, which is 0.0821 T for temperature. So now my equation is really just relating volume and temperature, which are the things I know something about and want to know something about. So I have my equation that relates my important variables. I take d dt of both sides. So I have 0.75 dV dt equals 0.0821 times dt dt. Now I plug in the things I know and solve for the thing I want. So I know dt dt is a half, so I'm going to put a half in there, and I'm going to solve for dv dt. So I have 0.75 dv dt equals 0.821 times a half. And then I just divide both sides by 0.75, and I have dv dt is 0.821 times a half over 0.75. And sure, that could be simplified, but I am not going to bother. My volume measurement here is liters. So my units are going to be volume units over time units. And my time units were seconds given earlier in the problem. So liters per second. With your binoculars, you watch as the space shuttle takes off. You are located on a viewing platform 2 kilometers away from the launch site. As the rocket thrusts upward, you tilt your binoculars to follow it, and once the rocket is 1.5 kilometers in the air, it is traveling 75 kilometers per minute. How fast are you tilting your binoculars in radians per second? Okay, so I've got some rates here. Traveling at a rate of 75 kilometers per minute. How fast? So this is going to be a related rates problem. We start by trying to draw a picture of the situation being described. So I have a rocket taking off. So this is the rocket on the ground. And then I am 2 kilometers away right here. So that's me. And then the rocket is going upwards. Um, and that distance is changing. So maybe we'll give that a letter name A because that distance is changing. This distance between the me and the rocket when it's on the ground, that's constant. That was 2 kilometers. And then this distance between me and the rocket, that's changing. Maybe we'll call that C. And this angle, theta, is also changing. And that's the angle of my binoculars with the ground as I watch the shuttle head up. Okay, so let's see if I can write out what do I know? What do I want? Okay, when the rocket is 1.5 kilometers in the air, it is traveling at 75 kilometers per minute. That's this distance changing. So dA dt is 75. We know dA dt is 75, and that happens when A is 1.5. Okay, and I want how fast am I tilting my binoculars at that moment? I want d theta dt when A is 1.5. So I need an equation that relates my important variables, things I know and things I want to know. I need an equation that relates A and theta. So I could use one of my trig relationships. I could use sine, opposite over hypotenuse, or I could use tangent, opposite over adjacent. I'm going to choose tangent because I like that this side is not changing. Just makes things less complicated. So I'm going to use tangent theta equals a over 2 as my relationship between my important variables. Then we take d dt of both sides. So the derivative of tangent is secant squared theta, and then times the derivative of the inside d theta dt. The derivative of 1/2 a is 1/2, and then times dA dt. And then I should plug in the things I know and solve for the things I want. But plugging in the things I know can be tricky. I need the secant of theta, and that's going to depend on the values of A and C here. Um, so secant is the reciprocal of cosine. So secant is going to be hypotenuse over adjacent. So I need to know what C is at the moment in time I'm interested in. So I'm going to redraw my picture. I know this is 2. I know this is 1.5. And I could find C by using the Pythagorean theorem. So 2 squared plus 1.5 squared equals C squared, and we get 2.5 is the value of C, which means that secant theta is 2.5 over 2. D theta dt is what I'm looking for. And that's going to be 1/2 times dA dt, which was given as 75. Okay, so the last thing I just need to do is solve for d theta dt. So 2.5 squared over 2 is 4 over 6.2 is 6.25 over 4. 6.25 over 4 times d theta dt. And half of 75 is 37.5. And so I'm just going to multiply both sides by 4 over 6.25. So d theta dt is 37.5 times 4 over 6.25. And that comes out to 24. And my units are going to be theta units over t units. My theta units are radians. My time units are minutes. They were given as in minutes earlier in this problem. But the question actually asked me how fast am I tilting the binoculars in radians per second. So I have to do a quick conversion by multiplying by a fancy form of 1. And I want my minutes to cancel. So I'm going to have 1 minute to 60 seconds. My minutes cancel. So I have 24 over 60, which is 0.4 radians per second. Suppose a paraboloid cup is inscribed in a hemisphere of a radius 4 inches. The volume of the paraboloid is given by 1/2 r squared h. For what values of the parameters r and h is the volume of the cup maximized? Okay, they use the word maximize. This is an optimization problem. So let's see if we can just, they gave us this picture. The radius of the hemisphere is 4. The height of the cup is h, and the radius at the top of the cup is r. There's a little r there. It's hard to see, but that's an r. R, h, 4. So the volume of the paraboloid is given by 1/2 r squared h. So the thing that we want to maximize is the volume of the cup, and that is 1/2 r squared h. And that's too many variables. I want to maximize this. I want to maximize volume, but I can only have one variable on the right-hand side. It's got to be an R or an H. So I have to figure out a way to get rid of one of these variables. So I'm going to use the fact that the hemisphere has a radius of 4, and I can draw in a radius anywhere. From the center of the hemisphere to the edge of the hemisphere is a distance of 4. And so I have h squared plus r squared equals 4 squared. That's my constraint. So this is my maximize equation. And then my constraint equation is h squared plus r squared equals 4 squared. That's my constraint. You use the constraint to eliminate a variable in your equation to maximize. So I'm just going to solve for this. I'm going to solve for r squared, which is 16 minus h squared. I'm not going to bother solving for r. I'm just going to replace the r squared here. So I have volume is 1/2 times 16 minus h squared times h. Distribute my 1/2 and distribute my h, and I get volume is negative 1/2 h cubed plus 8h. This is what I want to maximize. And the way we maximize a function is by taking its derivative and setting it equal to 0. That allows us to find critical points. And then we also need to check the endpoints of the domain. So I need to think about the domain of this function. Okay, and those are values of the input variable h. So h is the height of the paraboloid. So the smallest h could be is 0. And the largest h could be, if we're inscribed in a hemisphere of radius 4, the largest h could be is 4. In both of these instances, the volume of the cup would be 0. If h were 0, there'd be no cup, right? There'd be no, it'd have no height, and so there's no volume. And if h were 4, there'd be nothing, you couldn't have any width to the cup, right? If the height went all the way to the very, very top of the hemisphere, there'd be no way to build a cup. So both of these have a volume of 0. We'll keep that in mind for later. So to maximize, we take the derivative, we set it equal to 0. So v prime is going to be negative 3/2 h squared plus 8. We set that equal to 0, and we get h squared is equal to 16 thirds, which means h is square root of 16 thirds. Okay, technically it's plus or minus. I'm ignoring the minus because h can't be negative. Okay, it's not part of the domain. And now I just look at my chart where I put in h and volume. And I want to put in the critical point and the endpoints of the domain. So I'm going to put in a 0 and a 4. Those were the endpoints of the domain. And we discussed a couple minutes ago on the previous slide that both of these h values will give us a volume of 0. We can double check that by plugging in. If you plug in a 0 for h, you get 0 for volume. And if you plug in a 4 for h, you also get 0 for volume. And then my critical value is root 16 thirds. And that is going to give me maximum height. So if I put in root 16 thirds here, I'm going to get some number that is positive. I guess I could figure it out. Let's do it. So I have volume equals negative a half times square root 16 thirds cubed plus 8 square root 16 thirds. So if I cube this, I'm going to get 16 thirds, and then I'm going to have a root 16 thirds left over. So I'm going to have negative a half times 16 thirds is negative 8 thirds times square root 16 thirds plus 8 square root 16 thirds. So 8, that's 24 thirds. 24 minus 8 is 16 thirds, radical 16 thirds, which is a positive number. So that is how I maximize. So it said the actual question was what values of the parameters R and H is the volume of the cup maximized? So we know that H is radical 16 thirds. The R value, we had an equation that R squared is 16 minus H squared. So I'm going to get a new slide here. Okay, we have volume is maximized when H is radical 16 thirds and R squared is 16 minus H squared. So R squared is 16 minus 16 thirds. So that's 48 thirds minus 16 thirds, which is 32 thirds. So R is the square root of 32 thirds. All right, we have another activity for chapter 4 review, optimal pipe and squishy boxes. Pause the video, try these problems, and when you're ready to go over them, come back and press play. Your water company is building a pipeline to connect two towns to the Connecticut River. Each town is 2 miles from the river, separated by 4 miles. And you've decided to have one pumping station on the river to serve both towns. Okay, so we've got two towns, town A, town B, and they are 2 miles from the river, went like directly across from the river. So this is also 2 miles. Okay. And they are 4 miles apart from each other. Okay, so they are separated from each other by 4 miles, and they're both 2 miles from the river. Okay. We're going to put a pumping station somewhere along the river. If it could be right across from town A, and town A would have a very direct, only 2 miles of pipe that they need to lay. But then town B would have a much, much longer piece of pipe to lay. So the question is, if I want to optimize, I want to have the minimum amount of pipe, where should I put the pumping station along the river? So we're going to call this distance X, like the location where we put it is going to be X miles along the river from town A, and we're going to minimize the distance. So represent the length of the pipeline P as a function of X. So this distance, because this is 2 and this is X, this distance is going to be the square root of 4 plus X squared. And then this distance, I'm going to use the Pythagorean theorem again, and I've got 2 here. This distance is 4 minus x. So the hypotenuse is going to be 4 plus 4 minus x squared, and then square rooted. So P is said to represent the pipeline P as a function of x. It's this distance plus this distance. So the square root of 4 plus x squared plus the square root of 4 plus 4 minus x squared. What is the domain of P of x? So I'm going to put the smallest value of x and the largest value of x. So looking at the picture, the smallest value of x could be, we're measuring x as the distance from directly across from town A to some distance over till we get to town B. So the smallest x could be is 0. And the biggest x could be would be as if we put it all the way over here across from town B, in which case x would be 4. Okay, now I want to find p prime. So I'm going to take the derivative of this function. So I'm going to do treat the square roots as though they're 1/2 powers and use the power rule. And I'm going to have 1/2 times 4 plus x squared to the negative 1/2, then times the derivative of the inside, which is 2x. And then I'm going to repeat this process on the second square root. I'm going to have 1/2 times 4 plus 4 minus x squared to the negative 1/2, and then times the derivative of the inside, which is the derivative of this, because derivative of 4 is 0. So I just have to take the derivative of 4 minus x squared, bring down the 2, times 4 minus x to the first times negative 1. Number 4, if p prime of x equals 0, show that x root 20 minus 8x plus x squared equals 4 minus x times radical 4 plus x squared. So I've taken the p prime of x that we just found and set it equal to 0. And now I just need to simplify it a little bit. Okay, I just want to simplify this and show that I get this. Okay, so this function, I have a 2 times a 1/2. So those cancel. My 2 times my 1/2 cancels. 2.5. And then in the second term, I have a 1/2 times 2 again, and I can cancel those. So my 1/2 and my 2 cancel again. Okay, and then each of these can be written as a fraction. So I'm going to have 0 equals, I have an x on top, and in the bottom, I have radical 4 plus x squared. Okay, because I have a negative exponent, so I can move it to the denominator and make the exponent positive. And then instead of writing it as the 1/2 power, I wrote it as a radical. Okay, next term, I have a 4 minus x that can go on top. And then this factor should be moved to the bottom, but make the exponent positive. So this is going to be plus, actually it's a minus because I have that times negative 1. I've got this negative 1 here. So I'm going to change this to a minus. I have 4 minus x in the numerator. And in the denominator, I have a square root of 4 plus 4 minus x squared. I'm just going to multiply out what's underneath this radical, and I'm going to move this whole term to the other side. So I'm adding that whole term to the other side. So I have 4 minus x in the numerator. In the denominator, I've got a square root, and I'm going to multiply this out. So 4 minus x squared is 8 minus 8x plus x. I'm sorry, it's 16 minus 8x plus x squared. 4 plus 16 is 20. And then I have minus 8x plus x squared. So that is this whole term. I moved it to the other side, and I just simplified what was under the radical. This term just stays exactly where it is and how it is. And I have x over square root 4 plus x squared. And then finally, I can cross multiply these two fractions. So I have 4 minus x times radical 4 plus x squared, and x times radical 20 minus 8x plus x squared, which is exactly what I was supposed to end up with. Okay, number 5, I'm supposed to square both sides of the equation we found in 4. So I just copied it down here. I'm going to square both sides here. Squaring my x gives me an x squared, and squaring a square root just cancels. So I have 20 minus 8x plus x squared. And that equals 4 minus x. I have to square that. And then squaring a square root just cancels. Okay, and I want to solve this equation because this will be my critical points of P. So let's see, I'm going to distribute my x squared. So I have x to the fourth minus 8x cubed plus 20x squared equals, when I square 4 minus x, I get 16 minus 8x plus x squared, and I'm going to multiply that by 4 plus x squared. Distribute on the right. Okay, so I'm going to distribute my x squared, and I get x to the fourth minus 8x cubed plus 16x squared. And then I'm going to distribute my 4. So I just did my x squared to every term in the first parentheses. And now I'm going to do my 4 to every term in the first parentheses. So I have plus 4x squared minus 32x plus 64. And now I have some terms that are alike on the left and the right that are going to cancel. Okay, so I've got an x to the fourth and an x to the fourth. If I subtract that from both sides, those are just going to go away. And then I have negative 8x cubed, negative 8x cubed. Add that to both sides and those cancel. And then I have a 20x squared and a 20x squared on the right and the left. So subtract 20x squared from both sides and those go away. And all I'm left with is 0 equals negative 32x plus 64. So x equals 2. That's our critical point. And then we want to show that critical point as a global minimum for P by making an XY chart where I'm going to have x and P of x. And I just grabbed P of x from our previous slide. It represented the length of the pipeline, the full length of the pipeline. So I'm gonna make an XY chart, and I'm going to put in my critical value of 2, my critical point of 2, and also the endpoints of my domain, which were 0 and 4. And I want to calculate the length of pipe I need to lay to connect these two towns to the river for each of these x values. So if I put in 0 for x, this is the square root of 4, which is 2. This is 4 squared, which is 16. 16 plus 4 is 20, square root 20. So this is 2 plus square root 20. And if I plug in a 4, okay, so 4 squared is 16 plus 4 is 20. So this is square root 20 plus, and if I put in a 4 here, I get 0 squared, square root 4 is 2. So 2 plus square root 20 is the length of the pipeline for both 0 and for 4. And if x is 2, I'm going to put a 2 in here. 2 squared is 4. This is square root 8. And then 4 minus 2 is 2 squared is 4 plus 4 is 8. So square root 8 plus square root 8 is 2 square roots of 8. Okay, these are hard to compare without a decimal, so I'm just going to plug these into my calculator. I get about 5.65 for the length of the pipeline if x is 2. And then square root 20 plus 2 is about 6.47. Okay, so that means that this is the minimum amount of pipe that I will need to build the pipeline. So minimum pipeline length is approximately 5.65, and it happens when x is 2. At the dump, you work with a trash compactor and you notice that as a perfect cube gets squished, all 3 sides change length while the volume remains the same, as in the diagram below. So we have a cube, 2 by 2 by 2, and we squish it and it just gets flatter, but this gets longer, the height gets smaller. So the volume remains the same. Find the volume of the cube before squishing. So that would be 2 times 2 times 2, length times width times height is 8. Okay, which variables are changing and which are constant? So H, W, and L are all changing. Volume is constant. We're interested in the rate at which the length is changing. So write a relationship between the 3 variables to help find this value. So volume is length times width times height. Okay, but volume is constant. Volume is just 8. So this is actually 8 equals length times width times height. At the moment when the height is 3/2 and the length is 4/3, we know that the width W is increasing at 1/5 of a meter per minute, and the height H is decreasing at 3/10 of a meter per minute. Find the rate at which length L is changing. So I'm going to start by writing down what do I know and what do I want. So what do I know? I know dW dt, that is the width is increasing. The rate at which the width is increasing is 1/5 or 0.2. What else do I know? I know that um, the height is decreasing, so dH dt is negative 0.3. 3/10 is 0.3. And I want dL dt. And this is all at a specific moment in time when H is 3/2 and L is 4/3. So all of these, what I know and what I want, is when H is 1.5 and L is 4/3. So I start with an equation that relates all my variables. 8 equals length times width times height. And then I'm going to take d dt of both sides. The derivative of 8 is 0. And then I'm going to do the product rule for 3 variables. So it's not f prime g plus fg prime. When you have 3 variables, you take the derivative of the first one times the second two, plus the derivative of the second one times the other two, plus the derivative of the third one times the other two. So you can see I wrote LWH 3 times and I just moved the prime from L to W to H. This is the generalized product rule for 3 variables. Now plug in the things we know and the things we want. Okay, so I know W prime and H prime, and I want L prime. And this is all when H is 1.5 and L is 4/3, which means I should be able to figure out what W is at that moment. Let's draw a quick picture. Well, 8 equals length times width times height. Length is 4/3. Width we don't know. Height is 3/2. So 8 is 8W. So oh, sorry, 8 is 2W, so W is 4. So W is 4 when I have these other two quantities. So I have 0 equals L prime, which is what I'm looking for, times W, which is 4, times H, which is 1.5, plus L, which is 4/3, times W prime, which is 0.2, times H, which is 1.5, plus L, which is 4/3, times W, which is 4, times H prime, which is negative zero point 0.3. And now I just have to solve this equation for L prime. So 4 times 1.5 is 6. So this is 6L prime. And then now I just have a bunch of arithmetic with fractions here. So zero point 0.2 times 1.5 would be 0.3. 4/3 times 3/10 would be 4/10. Okay, and then these multiplied together, I have a negative here, so I'm putting a subtraction sign. So 3/10 times 4/3, the threes cancel and I'd get 4/10. But then I'm also times 4, so 16/10. And so I have 6L prime equals 12/10. So L prime equals 12/60 or 1/5. Okay, and my units for dl dt should be L units over time units. And was this, what were the length units? Meters? Yeah, my length units are meters and my time units are minutes. So this is meters per minute.